Okay, so I will find my slides first. Well, first of all, thank you very much, Willem, for the introduction. Thank you for inviting me here, both to Willem and also to the program chairs of ICAPS. It's really a big pleasure and an honor of being here for presenting my research activity. This is indeed a research activity that spans for the last 8 years, around 8 years, and it is about merging optimization and data science and machine learning in particular. First of all, the first thing that I would like to say are acknowledgements. So this is a joint work with some colleagues, some from the University of Bologna, like Michele Lombardi, that started from the very beginning work with me on this subject, then Alessio Bonfietti, Andrea Bartolini and Luca Benini, still from the University of Bologna. They've collaborated mainly on the application part. And then recently we had some very interesting collaboration with Matthias and Pascal. I don't know if they are here, I don't see you. But basically these are the people that have collaborated in some sense with me on this subject. So there is a lot of work going, a lot of research activity going on machine learning and optimization. And basically in two directions. The first direction is, that will not be covered in this talk, is about helping machine learning algorithms through optimization techniques. So there are very many research activities going on here. Yesterday during the master class of CPA-IOR we have seen some examples of this integration, and there is a nice survey in the book by Bessier et al. On data science and optimization. This talk will be on the other way around, so boosting optimization through the use of machine learning. In this field, this is not about all this research activity, because in this research activity we have many directions, okay? First of all, using machine learning for modeling purposes, and this is where this talk is positioned. And we have many research activity going on here, starting from CONAC by Bessier et al., Model Seeker, using intermediate language for learning modeling components through machine learning, okay? So this is a big area where empirical model learning, which is the subject of this talk, is about. There is another very interesting direction that is using machine learning for improving search, for boosting the search strategies. Yesterday we have seen a very interesting tutorial by Bistra Dilkin at the master class, and it was about enhancing branch and bound through machine learning techniques. In MIP. Then there are also other directions for using reinforcement learning for improving search strategies, and this is also a very interesting research area. And then maybe a more well-established research area is the use of machine learning for portfolio selection, where we have many algorithms and we have to select one of them depending on the instance that we have to solve, or algorithm configuration, so where we have to settle parameters of algorithms for improving their performances. And basically these are all very interesting research directions, but we will basically focus on the first part, okay? So we want to use machine learning for enhancing and helping the modeling activities. So basically traditional combinatorial optimization problems are modeled via optimization experts that interact with domain experts and to create a model of the problem that they have to solve, okay? So, and this is for a long time, it has been basically the main way of doing that. So now we have data. And so we can exploit this data to somehow learn some part of the model of the problem that we have to solve. Okay, so this is the very basic idea behind the use of machine learning for modeling. But before going into the details, I would really like to present 3 motivating examples, and then I will go into the details for one of them, because basically this is more related with allocation and scheduling. So being this talk given in also for the ICAPS conference, I think that this application could be more interesting for the audience. But basically I will give you 3 motivating examples that they have common characteristics and common features, and that make them very well suited for using and exploited machine learning for learning parts of the model component. Okay. So let's start with the first. We have a city. We are, say, the mobility manager of a city, and we have to basically decide where to put traffic lights over the whole city in the different intersections. Of course, they should be connected in some way, so there are constraints among traffic lights, so they can, for example, create green waves, so some intersections should be connected. And every operation has a cost, of course. There is a limited budget, and probably also other constraints that are not considered here, okay? So this is a traditional combinatorial problem. Basically, it can be a very large scale in case the city is big, but which is the toughest obstacle when we want to model it? The toughest obstacle is basically to assess the effect of a decision that we take, so the placement of a traffic light on a specific intersection on the traffic, okay? So this is why this is difficult, because first of all, traffic is a complex system. It is affected by human behavior, and basically it's very difficult to create a model that, a declarative model, expert design declarative model, that accurately represent this phenomenon, okay? So, but if we want to solve this problem, we have to extract this model. So we have to extract the relation between traffic light placement that we call decidables and traffic levels that we call observables. Okay? So we want to learn the impact on decidables on observable, and most important, cast this relation within a combinatorial model. Second example. In policymaking, I worked some years ago on a European project for policymaking, and basically, suppose that you are in a region and you want to target a given photovoltaic adoption to be achieved in the region, and you have to decide which incentives to give to households and companies for installing photovoltaic, for example, plants, okay? So the incentives, of course, have a cost. And there is a limited budget, again. There are many other constraints, for example, that limit the allocation of these incentives, and we want to solve this problem. Again, this is a combinatorial problem, which is the toughest obstacle. The toughest obstacle is basically to assess the effect of incentives on the PV adoption. And believe me, so we have talked with many governments in Europe, and they have no idea on how to shape and to craft the incentive mechanisms and to forecast the adoption, for example, of PV. Again, we have expert design declarative model. It's very difficult to be achieved. There is human behavior, social dynamics, and so on. So we want to, so if we call decidables the incentive design part and observable the PV adoption level, again, we want to learn the impact of decidables on observables and cast it into an optimization problem. Third example, this is where I would go a little bit more into the details. We have a target heterogeneous platform and a workload, okay? So a multi-core platform, an embedded platform, and a workload, so tasks that we have to run on the platform, okay? We are in the field, in the computing part. So we want to decide the dispatching of the workload on the resources of the platform and then possibly schedule it. And basically every task has a duration, it consumes some resources, but it has also a thermal dynamic, and the thermal part is very important because in general on these platforms there is a thermal controller that slows down things when the temperature goes higher with respect to specific limits. So we have thermal limits, and we might have load balancing constraint and other side constraints. So let me go a little bit more into the details. Why thermal management is important? Because basically the cooling cost in computing is increasing, so it accounts for almost 40% of the total energy demands in data centers, and it is growing. And beside the cost of this energy that is spent just for cooling, basically, this does not have a favorable environmental footprint. It does not, because it produces emission, and it is getting worse, okay? So basically, if we consider the supercomputer ranks by flops, we basically know that in 2020, the exascale scale computing will consume around 170 megawatt of power, which is basically the 30% of a nuclear budget for a today nuclear energy budget for a today nuclear reactor, and while the feasible exascale power budget is within 20 megawatts. So we have really to reduce drastically this power budget, and it goes, of course, by reducing the computing, the power of the computing part, but also of the cooling part. So the thermal considerations are really important. So, and these considerations should be done at very different scale from the data center to the single chip, okay, the single multi-core on a chip. And thermal management is very important also on multi-core systems. We have worked on this Intel SCC, which is a single chip cloud computer. It has basically 48 cores, a network on chip, and 4 memory controllers, okay, resources. But basically it has very serious thermal issues. Why that? Because basically overheating is really bad for these platforms. So because there is a risk for chip damage, reduced performance, reduced lifetime, and basically traditionally the thing is that we use controllers, thermal controllers on these platforms that reactively reduce the operating frequency when the temperature basically increases, okay? And this is, of course, poor performance. They even shut down cores. With combinatorial optimization, we can use a proactive technique, and we basically can dispatch the workload so as not to have overheating, okay? So the dispatching part, the decision part can be taken with an eye on the thermal part. So we need a thermal model, right? We need a thermal model, and a thermal model is built by taking into account that the temperature depends on the room temperature, the workload of each core, the chip fabric, the position of the cores and heat sinks, heat transfer between cores, on-chip thermal controllers, and basically, I mean, there are a lot of things that we have to do to take into account for designing a thermal model. But indeed, thermal models exist, and there are very effective computational models and simulators that somehow basically are very accurate, but they are very slow for being embedded into an optimization algorithm. So every time we run the simulator, it takes tens of seconds. So we want a declarative model that is an approximation of the thermal model, but that can be casted into a combinatorial optimization problem. So going back to our example, we need possible, we need to assess the effect of workload allocation on the thermal dynamics. And we want, of course, to cast this relation, so decidables are workload allocation, observables are core temperature. We want to learn this relation and cast this into an optimization model, okay? So these are three motivating examples, and what do they have in common? So all these problems have in common a strong combinatorial structure, okay? So there is a combinatorial structure behind, and this is a very important part of the picture. Part of this problem is not easily described through a manageable declarative model. So in the first two examples that I gave, basically extract a model of the impact of traffic light placement on traffic is very difficult because, I mean, even experts can tell us some, I mean, a very approximate model or even some heuristics. But in some cases, you have the model. For example, you have a model that mimics the thermal dynamic of the architecture, okay, by using differential equations. But of course, this is not manageable from a combinatorial optimization perspective. And also, we are not really interested in the whole dynamic of the temperature, but we want that overall the temperature is kept below a given threshold. Another very important thing that they have in common, decisions influence predictions and vice versa. So there are many, many problems where you use predictions for feeding an optimization component. For example, if you have to balance or to create the proper energy balance in a given house or in a given plant, industrial plant, you can take as input the prediction of the production of energy from renewable energy sources, okay? But your decisions do not influence the prediction. So the prediction on the produced energy by renewable energy source is not affected by your decisions. In this case, your decisions influence the observable, so influence the prediction. So when we decide to put a workload on a specific platform, we are influencing the temperatures, the prediction of the temperature. And of course, we want also the vice versa. We want that the prediction of the temperature influences the decision, okay? The same in the incentive mechanism design. So our decisions that are the incentives influence the prediction, so the PV adoption, and vice versa. So we really have to reason in a setting where we can basically somehow change the predictions because we are, deciding something. And we have to have access to data, okay? Historical data, simulated data, real data coming from the monitoring system to create basically a training set. Okay, so questions up to now? Is everything clear? Okay. So now we want to understand how to learn the relation between decidables and observables, okay? And this is the gist of machine learning, so why don't we use it? So we need to have access to the monitoring system, so to the data coming from our system. In the thermal example, these data centers and multi-core applications and multi-core architectures have produced data. Okay, produce many data that can be effectively used for monitoring the system, okay? And we can use this data to understand the effect of our allocation on thermal dynamics. So we have to create a training set. How can we create a training set? We start from observations, extracted from the real system, and we basically sample the space of possible workload allocations, and we observe the temperature after a while, okay? And we create this training set, workload allocation, temperature of each core, okay? And we do that for several samples offline, okay? So basically, when you have produced a training set, you can learn an approximate function that, via machine learning, that basically relates the dispatching decision with the temperature. So in this case, for example, we have 4 cores, okay, just to reduce the problem. We have these 4 cores, and we can design a neural network, 1 per core, that basically takes as input the temperature of the room, the current temperature, the average CPI, that is clock per instruction of core 3. Given the allocation of core 3, we are extracting some features of this allocation that can be used to feed the machine learning model that forecasts the temperature after a given delta T. Okay? So we can learn a model through data extracted by this architecture. In the core, for the core 3, basically features that influence its temperature are, of course, the CPI, so clock per instruction, which is a measure of the workload that I have assigned here, but also the neighboring cores, because the heat is basically traverses different core, okay, and the temperature is affected. So we have some, for each core we can create a neural network or any machine learning model that relates the features of extracted by our decisions and the observable. Then we want to cast this decision that we have learned into an optimization model. So we embed this, what we call empirical model, into an optimization model. So, in principle, there are different ways for doing that, okay? So, you can have a combinatorial optimization component, okay, that provides a workload dispatching, so decisions, and a separated black box solution evaluator that basically provides back an evaluation. So if the evaluation is fine, we are done. If the evaluation is not fine, then this component here should provide another solution, okay? And this can be very expensive. The black box evaluation can be a system simulator, for example, and this is a kind of a what-if analysis, okay? So I have a combinatorial optimization component, it provides a solution, the system simulator tells me if the solution is okay or not, okay? And then there is this iteration in a what if I do this, I take this decision. Okay, so in some approaches by OptQuest, for example, that dates back to 2011, provide a first improvement of this schema. So Lagoona provides basically a framework where you have here a scatter search, but it could be any other kind of search. Then a prediction of the simulator outcome, but still you have a simulator, and the predictor basically remove those solutions that have a trivially bad evaluation, okay? So it provides to the system simulator only those solutions that are likely to be interesting. Of course, instead of a system simulator, we can have a machine learning model, okay? Why not? See, if we have a training set, we can learn a machine learning model, and then we can use this machine learning model as an evaluator of the combinatorial optimization component. So this one provides the workload dispatching, and this one tells me the temperature, okay? And if I want to minimize the temperature or the maximum temperature, then this machine learning model is an evaluator of the objective function, or an evaluator of, the observable that we want to observe. And here we have surrogate models that indeed are doing exactly that. So they are learning models for evaluating a given solution as for the objective function. It can be maybe expensive to train, but after training, it is very efficient to use. Okay? So the evaluator is no longer a simulator that takes a long time for running, but the machine learning model is very, very fast and very easy to use. That this is a very good, but still a generate and test mechanism. So first we generate the solution, and then we evaluate, either with a simulator or with a machine learning model. What we want to do with empirical model learning is taking this machine learning model and cast it into the optimization component. This model should become active for reducing the search space of my combinatorial problem. Okay? So, this is a very important part. This is basically not limited to objective functions, but also constraint, and any relation between decide-ables and observables can be casted into this machine learning model. So this activity is subject of a recent AI journal paper that we have published in 2017 on empirical model learning. But I would like to underline one specific issue of this model when it is embedded into an optimization component. So why it is different from the traditional use of machine learning models. A machine learning model works forward. So when the machine learning model is considered as a mere evaluator, then I provide the solution, the workload dispatching, and the machine learning model provides me the prediction. This is a forward mechanism, okay? But the most important part of empirical model learning is that we want also the backward interaction. So we have our workload dispatching here, and of course this provides a core temperature as a prediction. But we want to, so for being inserted into a combinatorial model, and this is the most important slide of this talk, I want to be able to constrain that maximum temperature that I want to achieve and propagate back by removing those decisions that would lead to that would lead to inconsistent temperatures. So if my cores should be constrained to achieve a temperature which is not higher than, I don't know, 65 degrees, then I want this machine learning model to be active, and once it has been trained, I want the machine learning to be active and propagate back from these core temperatures that are now constraints of being lower than 65 degrees, to remove those combinations of assignment of workload dispatching that would lead to constraint violation. Okay, so this is the gist of empirical model learning. Okay, so then this is a very simplified combinatorial component of our problem. We have n tasks, m cores. We want to allocate each task on a core, on only one core. Then we can have some load balancing constraint and also other constraints like scheduling constraint. And basically we have that this is a combinatorial component, fully combinatorial component, a very traditional model. And here I want to insert a machine learning model. I have one neural network per core. And I basically embed this neural network in a combinatorial model component, this empirical model, which is, by the way, a problem constraint, okay? Or it can relate to the objective function. So I want to minimize the maximum temperature. So this learning of the temperature with the temperature with respect to the dispatching decision is part of my combinatorial model. Of course, it is an approximation, and we have to be aware of that. This is a very important part. So the third part is how to cast a machine learning model into a combinatorial one. So how do we embed machine learning models into a combinatorial model, and how do we provide the semantic, the operational semantic, the propagation, and the filtering algorithm to prune the search space. So we will say something about neural network, decision trees, and in the AI journal paper there are integration of these techniques into CP, local search, MinLP, and SAT modulo theory. In this talk I will just focus on CP. Okay, so you all know what an artificial neural network is. We have an input layer, an output layer, and one or more hidden layers. There are no cycles, at least for non-recursive neural network. This is a feed-forward architecture, and each neuron basically is a scalar function with a vector input. The vector of inputs are weighted, okay, and we have to learn this weight during the training part, plus a bias. And this is the activity of the neuron, A. And this activity is filtered by an activation function that basically provides the output of the neuron, okay? And the activation function is a monotonic, a non-decreasing function of the neuron activity. So we have inserted this artificial neuron, and this is a paper by in CP 2011. Basically, a neural network is a declarative nonlinear model, okay? So we can embed it, for example, in MinLP just by adding to the model the equations of the neural network. But in CP, it is a little bit more tricky. Why that? Because in CP, in general, we model these relations as global constraints. And we can have a global constraint for each neuron. So we have an activation function constraint that takes input variable, output variable, weights, and the bias. And of course, if we constrain the output variable, then we can prune on the input variable and vice versa. And the neural network is nothing else, basically, than a set of activation function constraints. You see here, there are some propagation rules. So given an internal variable A for the neuron activity that is basically related with the inputs of the neuron by this equation, okay, then we can have bound consistency on this equality, and basically we filter the activation function by every time the maximum of the activity of the neuron is updated, then I can propagate on the maximum of the output. And also on the other way around, when the maximum, so the output of the neuron is updated, then I can update the maximum of the domain of the input. So this is the propagation, back and forth propagation that enables to reduce the search space by using these constraints. And of course, there are similar rules for minima. If we put together these constraints, then we have a global constraint that is a full artificial neural network. So how it works at search time? At search time, we decide a specific allocation of some tasks to a given core. Then we extract some features and we propagate basically through the neuron constraints, we propagate that on the temperature of the different cores. Okay, and this is the forward propagation. We decide and we predict. But on the other way around, if we limit the temperature of the cores at a given threshold, then I want to remove those assignments, allocation of resources that would lead to overheating some core. So we have devised, I will go quite quickly through that, we have devised a model that takes decision variables and a load balancing constraint. This is a CP model. We have constraints that enable to create a feature computation, and this is a very important part. In general, machine learning models do not take decisions as they are, but we have to extract some features from the decisions that we have taken. Which is exactly the average clock per instruction that I was mentioning before. Then we put a neural network for each core, and we want to minimize the maximum temperature. The nice thing is that if we observe the real behavior of the architecture, we can also observe the behavior of a controller in case there is a controller on the architecture. So we can learn how not to, for example, switch on the controller that slows down the core frequency. And we have a paper in AAAI 2012 that was really about that. So learning the behavior of a system that is controlled by an external thermal aware controller. So these are some solutions. This is a set of heats generated on core on different instances via an expert design model by using MIP. And this is the heat generated by the cores by using the empirical model learning approach. So here we see some hotspots that are not good for the platform, while here you see that the temperature is much more homogeneous and much lower. So the thing is that an expert design model can provide some heuristic, and for example, they use load balancing as a heuristic, but basically these architectures are not homogeneous. So for example, there are cores that are closer to the cooling system, that are basically less prone to being overheated. There are some cores that stay on the corner of the platform and that are somehow can be basically more, have a thermal dynamic which is different from the core that we find in the middle of the platform. So all this heterogeneity is very hard to capture by an expert. So the empirical model learning can learn on each core its behavior and can adapt, of course, the decision to the specificity of the core. This is for neural network. For decision trees, basically we have also encapsulated decision trees into a combinatorial model. These are pretty easy. Why? That because decision trees are nothing else than implications, okay? So we have a paper at CPAIOR in 2011 that was embedding decision trees and random forests that, I have to say, do not work very well in a combinatorial optimization model. So this is a decision tree. So decision tree, basically at each node you have a test on a specific attributes, and in the leaves you have class labels, okay? So basically, given an example, we can find a classification because A equal to 30 goes along this branch, B equal to 20 goes along that branch, and then the class is equal to 1. So we can classify basically our examples, okay? So how to embed a decision tree in CP? We have a decision variable for each attribute, okay? So a decision variable for the class, and we can create a global constraint, as before, that relates the class with the attributes. But we want to enforce consistency on this decision tree, and this is the tricky part. So indeed, a path, we can have the different encodings. I will just show two of them here. There are many of them that we are collecting and putting together on a technical report that will be soon available. And basically a path is an implication. So A greater than 20 and C equal to 0 and B greater than 20 implies the class equal to 1, okay? Very easy. So we can simply put these, the tree defines all the paths. So for the class y equal to 1, we can simply have a disjunction of the three paths. This is the first, okay, which is this one. This is the second, which is this one. And this is the third path for achieving class 1, okay? We can simply put this implication into a CP model, okay? And this is very nice because it is simple, it is a polynomial size, polynomial time propagation, but it does not enforce generalizer consistency. So there are basically some values that are left in the domain and that are not part of any feasible solution of the constraint. But also this is also very suitable for SAT modulo theory solver. So can we do better? Of course, yes. So basically a path is a set of feasible assignments. So we can use a table constraint that is a very well-known constraint in constraint programming, and we can basically encode into a table constraint these three, okay? Of course, we have to discretize numeric attributes, and as thresholds, we use the thresholds that are used in the tree, okay? So we have attributes, and basically that can be casted into a table constraint, and we can use the propagation of the table constraint to enforce generalized R consistency. So on our 48 cores, 20 instances with almost 300 jobs, CP with large neighborhood search, and with the model learned via decision trees, and there are two encoding here. So the first one is the simple encoding and the second one is the table encoding, achieve basically better solutions, always better solution with respect to local search and with heuristics, and also basically the basic propagation helps with respect to local search, but a more tighter propagation, so a more powerful propagation helps a bit more. So we have also done other encodings, and they are basically in a technical report that we are going to submit soon, and that show on which problems specific technique of encoding is better with respect to another. So where they are trying to basically analyze different alternative encodings. Okay, so basically this is what I wanted to say. Now I would like to wrap up and make some final considerations. So empirical model learning indeed enables the solution of combinatorial optimization problems into domains where that are either overly complex or to model, okay? So like when we have to deal with a complex system where the expert design model is very tough to extract. And basically, or in cases where the model is there, but it is too complex to be used in a combinatorial model. So it helps in these cases. It is not, of course, the only solution, and it does not need to be about CP. We have used empirical model learning, as I was telling you before, also in other optimization techniques. CP is very suitable for empirical model learning for mainly two reasons. One is because basically it's easy to embed an algorithm within a global constraint, and the algorithm enables filtering. And it is flexible and modular, so we can add side constraints to the one that we have learned and obtain basically solutions, okay? So empirical model learning is a global constraint, and it is just a constraint. So it can be used together with other combinatorial constraints or other machine learning constraints. So CP is really very, very, very interesting. But there are some issues that we have to address to make it work. First of all, you can always use a machine learning or in local search, okay? So CP can work better because basically propagation helps a lot in reducing the search space, and you can use the learned knowledge in form of a global constraint to reduce your search space, okay? But for this, we need inference methods connected with machine learning models. So when we want to embed a new machine learning model into CP, you have to think about filtering algorithms for propagating backward and forward in the two directions. And this is very important. And this inference should be effective, so it should provide indeed tight bounds on the variables involved, and should be efficient, okay? So effective and efficient. And sometimes, I mean, you have to really find a trade-off between a complex machine learning model that provide you a very accurate approximation of the function that you want to learn, of the relation that you want to learn, but maybe have a very slow and weak propagation. I will give you a short example. Or you can consider simpler machine learning models that are, oh yes, less accurate. You have to be aware of that, but then whose propagation is effectively. But then you run the risk of having good solutions that are not so realistic. So you always have to find a trade-off between accuracy and efficiency. So you have to characterize this accuracy optimization trade-off. We have to find design rules, and these are open questions, okay? We are, for example, trying to encapsulate a deep network into global constraints, okay? So we have this Google Faculty Award that is devoted to that. And so deep networks are very accurate. They will provide very accurate predictions, but encapsulating them into a global constraint is really, really tricky. Why? Because basically the same reason why backpropagation alone does not work on deep network is because the gradients are vanishing toward the layers. And the propagation does the same. So basically, if you constrain the output of the network, then the propagation to the input layer, that are your decision, is very weak. So we are trying to create other alternatives for achieving better propagation. So also there is another issue that is very interesting. So you learn basically, a machine learning model provides you, given a set of data, that these green spots here, provides you a prediction for every input value. And basically, here the prediction, for example, for the final solution is this one, while the real value could be this one. So there might be a large error when the solution that you find is far, for example, from known examples, okay? So there are some techniques that can be borrowed by the design of experiment field to select good examples and to sample the data space for giving to the machine learning model good examples, and also you can use active learning to adjust the function that you have learned during when you have new solutions, when you have new data, basically, okay? So when you find a new solution, indeed, this is a new data point, okay? So for which you have the true value because you can experiment it and you can insert it to improve your machine learning model, okay? Okay, so fourth issue, and this is also a very interesting research direction, I think. Machine learning model provides you, confidence level, so it gives you an idea of the approximation of your model, and basically you can take this information into account when optimizing. And for example, some machine learning model can deal with certain inputs, and you can employ empirical model learning in stochastic optimization, for example. So you take into account the uncertainty on the output and possibly on the input in the optimization part. Also, you have to be aware that some errors are more important than others. Just very, very quickly, if you underestimate the temperature, then, so if you overestimate the temperature, you can come up with a workload dispatching decision that is suboptimal, okay? So you could have been done better. But if you underestimate the temperature, you may run the risk of having a solution which is infeasible, that will damage the platform. And so you have to be aware of that, and you have to take into account this while optimizing. And this is also another research direction we are working on. And probably the toughest issue of all, optimization researchers like clean and declarative models, while machine learning researchers seldom use decisions as input for their models. So we really need to work together and bring together research activity in constraint programming, machine learning, OR methods, and show basically that optimization on real-world systems is possible, is doable, and this requires cross-fertilization and the effort from everybody. So I think this is it. Thank you very much for listening. I don't see anything. you want this? Okay.
I want this, yes. I think it should be on. Thank you very much for an excellent presentation. We now have time for a couple of questions, and I will make sure that we have time to leave this room and go to our respective rooms.
Okay.
We have a special feature here. I think it should work if I talk into this cross here. So far it doesn't work, but we can throw this to people that have a question, and then you can talk into this box rather than passing a microphone around. Now, I cannot really see you, so I think I'll step down, and I open the floor for questions. So if you can raise your hand or just shout, I can... There we
Okay,
go.
thank you. Now I see you.
Who wants to ask the first question? There are many questions on that side, so I'll walk a bit, but
Okay,
I
and
cannot
then
throw
you
that
throw.
far.
Okay.
Okay, it should go somewhere there, okay? There we go. You should talk into the cross, if I'm not mistaken.
Hello?
Yes.
Okay, it works.
Wow. It works.
So thank you very much for the really excellent talk. I think this work is fantastic. One of the situations I run into a lot is that we want to optimize over simulations which are very computationally expensive. So just getting the enough training data for a high-resolution model is not possible. And I would guess your complex system example, like the traffic, would kind of fall into that category. So could you just talk a little bit about if you've had experience with that, and if so, how would you recommend dealing with it?
Yeah, I mean, this is a very good question, a very good point. I mean, indeed, basically we can, so when we have a simulator, basically we use the simulator to create a training set. So definitely there is the issue of deciding which sample to use, so which simulation run to use to create a training set which is accurate enough for describing your phenomenon. So indeed this is an open issue, and in this case we can borrow some concepts from I mean black box optimization and design of experiment to try to understand which are the proper samples that you have to extract for creating an accurate model. But this is definitely a very important issue. That, I mean, it is open, of course. It is. There's not a.
Another question? That's great.
This is not my first encounter with the box, actually. So one of the questions I have about your learned function for the temperature, you need to predict the temperature not only now but into the future.
Yep.
Right? So this means that, you know, how you learn the model is almost as important as the fact that you've learned it and integrated into CP. So did you encounter difficulties in figuring out what to learn?
Yeah, we have done several tests. Indeed, basically in principle, you have not the guarantee that between the time I take a decision and the future prediction, the temperature will never exceed the prediction, that, so basically the threshold that you imposed. But yes, I mean, this is finding the proper predictor or the proper thing to predict or the proper indicator to predict is part of the modeling activity. So indeed the modeling activity seems to be simplified by this, but it is not, because also extracting the proper features for predicting a specific value is very tough. I mean, it's the most time-consuming part of the overall thing. So basically, there are two things that we have to define. First, what I want to predict, which is a modeling choice, and what to use for predicting those basically as input to the model that are features extracted from your decisions. So there are two things that are pretty I mean tricky, that would complicate the modeling part.
That's what's the box.
Can you give us an idea of how deep or wide are the models that you use for your different experiments?
Sorry, what?
What was the size of your models?
The size?
The size,
Okay.
sorry.
Well, the size, I mean, this example of the core of the workload dispatching on a multi-core, so basically the combinatorial part is that you have a number of variables that is equal to the number of tasks, like 300 tasks, and you want to allocate them on 48 cores. So this is the combinatorial part. Of course, and the neural network is very tiny, very small, because in the neural network you have, and so it is also fast to train, because each neural network looks locally at each core. So in each core you have the input of the core, the workload dispatching of the core itself, of the neighboring cores, because they are affecting the temperature of the core, but the neural model is really small. It's really small. So it is fast to train, and it looks locally at each core. So it is a kind of an observer on top of each core that observes the temperature on the core, but it is small. Then you can insert this into also a larger combinatorial model, because basically you are observing locally each core. In this specific example, then you may have many other examples of different size, different dimensions, of course.
Okay, thanks.
Thank you very much again.
Thank you. Thank you.